Good afternoon, everybody. Everybody in the room and everybody online. I'd like to welcome you to this talk and also to welcome Francisca. So you all know who our speaker here today is, Francisca Martínez Hergueta. Francisca is a lecturer at the University of Edinburgh. Before that, she was in Oxford, in Nick Petrinich's group that many of you know. And before that, she did her PhD at INDEA in Madrid with Javier Llorca and Carlos Gonzalez's group that also many of you will know. So she has worked on high velocity impact for a large number of years, well, not very large, a small number of years, but what she's going to talk to us about today is automated fiber placement. And so without any further ado, I'll leave the floor to you, Francisca, and thank you very much for coming.
No, thank you very much for all of you for inviting me to come here today. I'm very, very happy to be at Imperial. I hope everybody connecting online can also hear me. So this is myself. Today I'm coming to present the work of my first PhD student in impact response of advanced placed ply laminates that I will explain soon what they are. Before starting with directly, what we have. Let me, what? Now, okay. So before starting with the research presentation, I wanted to introduce myself. I'm Spanish. I'm coming from a very tiny town in the center of Spain. It's called Albacete. If we translate that into Scottish or Gaelic, it means the Scottish town. So that should have told me a little bit about my future. I didn't know that at that time. I did my PhD in Madrid at the INDEA Materials Institute, working with this amazing team of people, Javier Llorca, Carlos Gonzalez, and Claudio Lopez, on impact response of materials. And after my PhD, I moved to Oxford to work in the laboratory of Nick Petrinic. You might see a couple of faces, you know, on that picture. And in 2018, I took a lecturer position at the University of Edinburgh, in particular in impulsive dynamics. As my work as lecturer is divided in different blocks, I've got a 40% of teaching load that I spent teaching a 5th-year course in dynamics on impulsive response of materials, which is very, very cool, where I taught ballistic response of composites, wave propagation, and all that cool stuff. But I'm also taking care of first-year students with a role that is called cohort lead, where I provide academic advice and pastoral care to them. Apart from that, I also have a 30% of admin load. I'm part of the postgraduate school. I take care of the progression of PhD students, also providing advice on different processes, internal processes that we've got, and also providing pastoral care as much as I can. And I'm also academic supervisor of a team of amazing people. This is a student-led team that is manufacturing and developing their own rockets. 1 month ago, they participated in a European context in Portugal, where they launched their rocket successfully. We were the fastest ever from a Scottish group. Very, very proud of them. The rest of my time is within research, and my research line focuses on experimental and numerical characterization of impact response, mainly on composites. So myself, I sit in between 2 different research groups. So it's the composite research group that is led by Professor Conjoro Brody, and the impulsive and structural dynamics group that is led by Philippe Teixeiras Diaz. So my research lines right now, I've got 4 PhD students working on 3 different topics: 3D printing, low-cost composites, that includes a huge bunch of things, and the topic that I'm coming to talk today, which is damage-tolerant composites for high-value applications. So as I mentioned before, this is the work performed by my first PhD student, Rutger Koch. He came here to Imperial some months ago, so some of you might have know him. He worked on a new preforming method that can be implemented using automatic fiber placement. I guess the main context for this research is something that is very much shared by many researchers at Imperial, which is the susceptibility of composites when they are subjected to out-of-plane impact loads. So we know that when we subject these composites into impact, they quickly lose their in-plane mechanical properties, in particular tensile or compressive strength, for example. So, sorry. In the literature, we always find approaches to reinforce in the through thickness direction all those structures. The issue that we have is that they all result in a lower performance in plane mechanical properties. So generally, all these three woven composites, they present a lower stiffness and a lower strength in comparison to some others. So automatic fiber placement brings us new opportunities to exploit new concepts in composites with improved mechanical performance and impact tolerance. This is something that was developed some years ago in Delft University. How does it work? So this preforming method, instead of staking all the layers of the composite in a conventional angle-ply laminate, they interlace different tapes in order to create this preform, which looks like a woven, a macromechanical woven. How does it work? It works by laying up different tapes. So what we do is to lay up the tapes leaving a certain gap. So what these gaps allow us is to create the preform, introducing a reinforcement. What is the disadvantages of this technique? The main disadvantage is that it takes kind of lot of different steps to create a laminate that otherwise you will be manufacturing with 4 steps that would be over. But the aim of this research is to explore whether there is an advantage in using these preforming methods when we would like to improve our damage tolerance. So as I said, this was already investigated previously and developed by Delft University, but their scope was rather limited just in the development of the technique. The research objectives that we want to propose for this job is to focus on the characterization of the deformation and failure mechanisms to provide a better understanding on what could be the response for impact. So, but knowing that, what we would like to do is to improve the design and the architectures of these composites to enhance their damage tolerance. In order to do that, we also would like to propose some numerical tools that can help us to assess those failure mechanisms and provide us a tool that we can use for stress analysis of large components. In order to do that, we propose the following program. So first step is to determine which are the micromechanisms there. So we have proposed some micromechanical characterization. Afterwards, I will go through the numerical modeling methodology. Subsequently, we've got some quasi-static characterization to validate our models. And later on is where I will introduce the relevant topics for this talk, which are the dynamic and impact response of these composites that are mainly the novelty of this thesis. So the micromechanical characterization, we directly focus on the response of these undulations that are repeated over these AP-PLY composites. We manufacture a laminate that introduced one of these undulations, and we can observe that there are 3 different sections over there. So I'm pointing here now. Our tensile direction, our loading direction, was axial to this undulating toe. So that's the direction of testing. Then we also have non-undulating toes that are perpendicular, and we always have a resin rich region that is originated somewhere near here through the resin flow. This micromechanical characterization was performed in a tomograph in Manchester through a grant obtained by Fibre. And these are more or less the results that we obtain. So we measure the crack density for different loads, so at different steps, until final failure that was in between 1500 and 1600 Newton. It's going to be a little bit difficult to see it. Maybe the main failure modes that we characterize for these loads is matrix cracking. All these cracks, they are appearing perpendicular to the loading direction, and they increase exponentially with load. But what I would say is interesting to appreciate is that the first crack is originating exactly on the undulating point. That means that the undulations are going to present the strain gradients that are going to have a detrimental impact on the strength of these composites. We can already see that happening here. All the rest of the cracks, I guess it's not as maybe in the screen it's easier to see it. They are all mostly perpendicular. This is not the same study. This was an MS thesis. It's not exactly the same laminate. It's missing a 90-degree layer on top and bottom of this. But these figures allow us to characterize further failure modes. So we can see that the catastrophic failure occurs due to fiber tension, and it's on very, very specific points. If you analyze it by finite element analysis, it is clear that damage is triggered on points that have particularly large strains. There is a very large strain gradient originated. Another failure mode that we can appreciate that has been triggered mostly at the same time as fiber failure is the lamination. So all the previous cracks that were perpendicular to the loading direction, they go through the toe and they originate this characteristic, the bondings. So what we end up is with a structure where all the toes have been debonded. This means that these laminates, they present three different failure mechanisms that are relevant and that might need to be included in any numerical model. Is matrix cracking first, and then afterwards we've got a toe debonding of the lamination and fiber failure to represent. So with that information, we try to recreate a model that could capture all that mechanical response. But the first issue that we face is that the geometry of the AP-PLY laminate is already quite complex. So when we are lining up tapes, individual tapes, we end up in undulation geometries that might not be straightforward. You might be able to predict the second layer, you might be able to predict the third. When you interlace more and more, it just gets way more complicated. So in order to conduct such research, we proposed a multi-scale model that was simplifying the undulation regions, creating an idealized geometry that includes a particular undulation region that I will explain later. All the rest of the material is represented or modeled as a conventional composite, as has been always done, where we just include the material toe as it would be on a conventional Fibre in a conventional way. These undulating regions can be represented with 4 congruent sections that contains either 2 toes or either a toe and a resin rich region. So some of those toes in these unit cells, they are undulated. We have introduced the undulation following the equation over there as an average 3, and they work as unit cells. So we consider which is the volume of each material in each unit cell, and we do the volume integral in order to homogenize the response. The undulation itself, they can be represented with 2 unit cells. The rest of the unit cells, the straight fiber toe and the rich region material, those represent the rest of the material. When you use this approach, the main advantage is that the undulations, they can be represented with 4 single elements. So this is what I'm showing in this figure over here. You can see the white regions, they represent straight toes, regular material. All the rest of the regions, they represent the interfaces. There are a lot of colors, mainly because there are a lot of different configurations. So angles crossing over. And that is what we represent. The main message here is that number of degrees of freedom, number of elements is relatively low compared to a micromechanical approach. That means that this approach can be implemented for large scale applications and large models. We were talking before that we wanted to introduce as well the failure mechanisms. The failure mechanisms can be implemented using any single model that you would like to apply. Rutger tried thousands of them. These are the ones that gave us better stability for impact. So our intralaminar material behavior is included with two different models, a tow model and a pure resin model. The tow model is a transversely isotropic model, the conventional one, with a 3D Hassing failure criteria. It might be not the most accurate one, but what we find out is that it was quite stable. And that's why we finally went for this one. Damage dissipation, exponential and linear lows depending on the failure mode, and those are described over here. We've got some exponential lows for fiber failure and some triangular lows for matrix cracking. That means that this model has already implemented two of the main failure mechanisms we described before, matrix cracking and fiber failure. We are missing toe debonding. For toe debonding, we just implemented the cohesive surfaces that are already available in Abacus, as this could have been done for a regular angle-ply laminate. So all these approaches that I have presented is available in this paper published in Composites Part A, and there is also a link to a GitHub that contains all the software that Rutger has developed to implement this. The software contains Python scripts that creates the geometry and the meshes, and it also includes the subroutines that he has been using. So they are open source. Everybody feel free to go for them and investigate and use them. He just asks for reasonable acknowledgement and citations if anybody wants to use this material. And he's happy to be contacted if there are any questions about it. So once we have that, the first thing, of course, is to validate our models. And in order to validate, we have manufactured our two first advanced placed ply laminates. But in Edinburgh, we do not have sadly an AFP machine. So Rutger manufactured them by hand. You can see there the work he performed. So it was tedious, but it was okay. So he designed two different preforms, a quasi-isotropic one with angles at 0, 45, 90, and minus 45 degrees, and a cross-ply laminate at 0 and 9 degrees. Toe skipping parameter, which just reflects the number of toes that goes in between the passes, is 3. That can be defined and can in the paper, we have explored what happens when you change that skipping parameter. We also manufacture some baseline angle-ply laminates, just using conventional layers for reference. The material that we employed was a carbon fiber epoxy Fibre, and we manufacture them by hot pressure in a hot plate press. So something to mention before going into the results is that since we are using tapes to create a mesostructure, we might end up with relatively large representative volume elements, and we need to consider them when creating our coupons. So we might need to adapt the current standards that we are using in order to be sure that at least one representative volume element is contained. That means that our samples are slightly bigger than the conventional ones, with 40 millimeters width. And these are the first results that we obtained experimentally, which is the comparison in between the baseline angle-ply laminates and this AP-PLY response. The first finding is that there is not an impact on stiffness. Doesn't matter which configuration you try. The cross-ply and the quasi-isotropic laminates, they present the same stiffness as the conventional composite. In terms of strength, you find different answers when you go for different laminates. So the first one, the cross-ply, what we obtain in this point is a lower strength. The lower strength is directly related to the ondulation strain gradients. So what we find out is that these ondulations, they are detrimental for strength. When they are subjected to axial loading, they are gonna increase the local strength stresses on our toes, and they are gonna trigger damage early. But we do not have the same when we evaluate the quasi-isotropic laminate, but that has to be also related to the failure mechanism. So these quasi-isotropic laminates, the first failure that occur is not fiber failure, is matrix cracking. At that point, what we will have in a conventional laminate is a matrix cracking of the 90 of the layers oriented at 90 at 45 degrees, and that will originate this softening that we observe. That did not occur in the AP-PLY laminate. The AP-PLY laminate was directly, it was linear elastic until final failure. So in order to explore what was happening and why the difference in mechanical response, we also employed our numerical models, and first we validate them. This that I'm showing is just the validation of the numerical models. So we conduct the, we conduct the numerical characterization, and we analyze what was the response against the experimental. We can see that in any case, we are always capturing the stiffness. In the case of the cross-ply laminates, we can also capture decently the maximum strength and the reduction in strength due to the ondulation. In the quasi-isotropic laminate with the baseline, we can also capture the softening due to the matrix cracking. It's a little bit more complicated to capture the strength of the AP-PLY laminate. That's because our models, since they've got a reduced number of finite elements within the undulation regions, since the complexity of the architecture increases, also the accuracy of the multi-scale model decreases. But let's say that we are still in a decent range. So we use these models to give some understanding of what was the response of the laminates. It is evident that the cross-ply laminate failed due to fiber failure. We can predict the knee cracks that they occur through the ondulations. But it's also interesting to appreciate which is the pattern of matrix cracking over both laminates. So in a conventional cross-ply laminate or a conventional quasi-isotropic laminate, we will find out that matrix cracking is spread all over the laminate. In this case, all matrix cracking is within the toe boundaries. That means that the ondulations are acting as crack arrestors. And that gives us some hope that this might behave better on impact and might present a better damage tolerant response. That's the hypothesis that we've got for the improved response of the quasi-isotropic laminate. It also develops cracks, but since they are arrested within the toe boundaries instead of spread all around the laminate, they result on a linear elastic response. That's something that we might have seen sometimes in wovens. Wovens composites, they behave linear elastic until the onset of damage, despite they have been cracked all over. If you go for some investigations on acoustic emissions, there's definitely quite a lot of matrix cracking, but you cannot appreciate it directly on the when analyzing the stress strain response. This is more or less what we appreciate here. So that's already an initial advantage of these composites. Any questions up to this point? So now going through the dynamic characterization, this is definitely the novelty that was not investigated before. So you might have here that composites that has defects, they might have a detrimental response on impact. These defects, they might increase their evidence when they are subjected to high strain rates. And definitely an ondulation can be considered a defect. So we wanted to investigate whether high strain rates might be detrimental for these laminates, but the issue is what I mentioned before. In order to be sure we are really characterizing the response of the parent laminate, we need to go for very, very large specimens. And in the UK currently, our split Hopkinson bars, they are miniaturized. They use very, very small specimens to characterize the impact response. So we needed to do a joint effort with the University of Oxford to apply for some European funding to be able to access the world's largest split Hopkinson bar, which is in Italy. It has steel bars of 100 millimeters diameter and a length of 100 meters. And it allows you to basically characterize the response of very large structures and components, such as the ones that we were proposing here. We characterize the response at 25 seconds to -1, which is usually the strain rates that you might find for low velocity impact, which is the main investigation of this work. So the first results, the first finding, when we compare the AP-PLY laminates with the baseline laminates, these are again the cross-ply and quasi-isotropic laminates that we have shown before. They just have higher thickness, but it's the same structure. We can appreciate how stiffness, it's still looking like the same. There's not a difference in stiffness between the AP-PLY and the baseline configuration. But very interestingly, in both laminates, cross-ply and quasi-isotropic, we find the same strength. So that means that basically the detrimental impact of the undulations that we appreciated in the quasi-static regime, they are not as relevant for the dynamic regime. So these are more or less the samples and the failure modes. Of course, we've got main failure mode is fiber failure. There's also quite a lot of matrix cracking, but there is a slightly difference in failure modes and how they are triggered that results in an improved response. The first one, it might be a slightly higher strength of the epoxy resins that might delay the matrix cracking that it was occurring. But there has to be also a difference in the dynamic fiber realignment. So the strain gradients, they increase in time as the toe realigns. When we do this on a dynamic basis, we don't give time for that toe to realign. That means that the strain gradients that we were generating before, they don't have such a high magnitude. So those mechanisms, they tend to compensate such that at this dynamic regime, there is not such a high difference in tensile response on the cross-ply laminate in particular. So this is a little bit of the future work to be done. Further investigation on the dynamic fiber realignment will really shed further light on this. But nevertheless, it gives a good opportunity to further investigate in these materials for aerospace applications. And finally, this is what I initially came to share, which was the impact characterization. This was finally manufactured on a real AFP machine in Madrid. So there is a foundation for composite materials there. It's mainly sponsored by Airbus, where they've got an MTORES equipment that we use to manufacture these composites. This machine has 8 channels for toes. The approach we used to manufacture the AP-PLY laminates was to empty half of these channels in order to create the gap. So the gap that we are using here is not 3 toes. We are just leaving one single gap. That means that if our machine had 8 channels, we were just using 4 of them. The panels were manufactured in carbon fiber epoxy, but we used dry toes that then we infused with the resin on our vacuum bath. We manufactured cross-ply and quasi-isotropic laminates as before, but we also include a third configuration, a triaxial configuration, 0, 6, and -60. The experiments were conducted at Carlos III University of Madrid, that has one of the biggest impact laboratories in Europe. It's also mainly sponsored by Airbus. We tested at 2 different impact energies of 30 and 50 joules of energy. And we also conducted compression after impact experiments in order to assess if there was any advantage of these technologies. Before going through, I wanted to mention that we manufactured the AP-PLY, but we didn't have resources to manufacture the conventional laminate. That was due to budget restrictions. It was a tough call, but this is the way we needed to go through. And these are the first results are the force displacement curves. The first good thing is that apparently there is not a massive influence on the impacted point. All the curves, they are quite repetitive for all laminates and for all impact energies. The triaxial and the quasi-isotropic laminates, they perform very similar in terms of stiffness and maximum loads. But the cross-ply laminate present a poorer impact response. In particular, it reaches a maximum load capacity of around 12.5 kilonewton. And this plateau indicates that with 50 joules, we have activated a catastrophic failure mode definitely. In terms of, so together with the experiments, we also analyzed the response numerically. We couldn't find any fiber failure for low velocity impact. And the main failure modes that we characterized were matrix cracking of the directly impacted toe, and then toe debonding as we were moving away from that impacted toe. So this really makes us think that the cone undulations acting as track arrestors before quasi-statically, they also have a similar effect under low velocity impact. When we evaluate the performance, we mentioned that all the laminates, they were behaving pretty much similar. When we evaluate the delamination footprints, that's something that we can also find. They all present a rather circular or elliptical footprint, except for the cross-ply laminate impacted at 50 joules that has a much larger delamination extension here with a cross-shaped footprint. This means that the catastrophic failure mode that we activated and we mentioned before is delamination. Our numerical model, unfortunately, couldn't capture that failure. There is a reason for that. So delamination is driven by shear in plane stresses, and those shear in plane stresses for the AP-PLY laminate are mainly originated in the undulations. So as you know, a strain gradient to be well represented needs lots of elements. And instead of using lots of elements, we are using just 4. That means that we can predict there is a gradient. We will see a difference in strain, but we cannot predict the magnitude. We are limited on that. Our model is very much optimized to capture fiber failure rather than lamination. In the literature, you will find approaches, micromechanical approaches, that are very, very good at capturing this interlaminar delamination, but they use massive amounts of elements, and they are more indicated to be used at materials level. So at this point, if you're going to investigate AP-PLY laminates, you need to make a decision on whether you're going to investigate at materials level. You might want to go for a micromechanical approach, or whether you might want to develop tools for industry and stress analysis, where you might want to go for one of these macromechanical approaches. Another point is that since we've got numerical models, we use them also to evaluate virtually the response of conventional angle-ply laminates. We didn't manufacture them, that's part of our future work, but at least we did some numbers, and what we find out is that the predicted delamination footprint of the baseline laminate is larger. So that gives us some hope that the AP-PLY laminate will perform better on impact. What we can really declare here is that there's an advantage on triaxial and quasi-isotropic configurations. They can retain the extension of the lamination compared to a cross-ply laminate, and also compared to conventional angle-ply laminates. At this level of energy, 50 joules, it is very unlikely to have delaminations that are this size or rather this small. You will find instead a very widespread delamination, in particular on the rear back faces of a laminate. So finally, just to end up, this is the last experiment, is compression after impact. In compression after impact, we find out 2 different trends. The triaxial and the quasi-isotropic laminate, they had a pretty good response when subjected to impact, when they were just losing up to a maximum of 26% of the residual strength capacity for a 50 joules impact energy. There is a marginal better response of the quasi-isotropic laminate, and that's probably related to the higher spread of angles that we are using. That's something that is also extrapolated from general angle-ply laminates. We have seen that on low velocity impact, they tend to behave better when they've got there is a smaller mismatch angle between layers. This is something that we are also evaluating here. Marginally, the quasi-isotropic laminates, they've got a lower mismatch angle between toes, and that results in a better stability and a lower delamination footprint. The laminate that has a different trend is, of course, the cross-ply laminate, with a reduction in strength, compressive strength of the 49% when subjected to 50 joules of energy. So one of the bits, of course, why it's performing worse is the larger delamination footprint, but it also has to be related to the main failure mechanisms that are triggered. So the cross-ply laminate presents a very, very low stability to compression and presents a very clean crack all over it, very, very straight. On the other way, the triaxial and the quasi-isotropic laminates, they present diverted crack paths that follows the toe geometries. So this results in a better strength and in a better energy absorption capacity, let's say. There is another point to mention here, and it's the level of reinforcement. So the cross-ply laminate, since we are interlacing layers, it's created of sublaminates. So in the cross-ply, the sublaminates, they just contain 2 layers. In the triaxial and the quasi-isotropic, they contain 3 and 4 layers. There is a higher level of reinforcement there. And that probably also gives us an advantage when we deal with the quasi-isotropic laminate. And yeah, this was my last slide. I think this is just right on time for questions. So as summary, we evaluated which was the mechanical response of different AP-PLY laminates, and we set some light on the main deformation micromechanisms. We find out that the response is slightly better at high strain rates, mainly because the undulations, they can act as trap arrestors effectively. That will end up in lower delaminations when subjected to trough-weight power impact, with a better stability of a compression after impact response. That was the job performed over 4 years of a PhD student, and of course there is no thesis that ends up having no future job. So we didn't evaluate all the possible scenarios that we might find on these kind of structures. Compression loads are quite relevant, that is something to be investigated. The AP-PLY architecture can be combined also with conventional angle-ply laminates, which are much cheaper to manufacture. So it can be interesting to evaluate how to use this and optimize and the application of this for different scenarios. Numerical modeling can be improved. Shear responses, matrix tracking, the lamination, there is a scope there to improve the response of our models as well. And then the models that we have used, they are able to provide a prediction, but so far we have not implemented an optimization framework. That's really something to be done. So if you are in a company, your question will be, what will you give me for this problem? And that's something that we could work towards in the future in an optimization framework that can give you the actual better configuration with better response. So that was all. In acknowledgements, I would like to acknowledge my colleagues in Oxford who got the funding to access the European facilities. Partially, this research has been also granted by Royal Society, one of the research grants to get equipment. And additionally, we also got a Henry Royce Institute, and this was Rutgers, that supports PhD students and provides access to different equipment. If you are a PhD student, you are looking for a facility, this is something you would like to look at. It also looks nice in your CV because these grants, they are given to you, not to your PI. So this is a box you might want to tick during your PhD. Nothing else to mention. If you've got any questions.
Thank you very much, Francisca, for this very nice talk.